Okay, so now we're going to talk about exponential functions, which may not actually be the ideal order, but that's the order I'm going in. So an exponential function is one that looks like a times b to the x. That doesn't look very good. A times b to the x. And b has to be bigger than 0. The reason b has to be bigger than 0 is because if you take, for example, negative 1, if you take it to the 1, then it's negative. If you take it to the 2, then it's positive, negative 1 squared. If you take it to a fractional power, it's undefined, because like you can't take the square root of it. A cube root, you could. So it'd kind of be all over the place. So the graph would be some places whole, some places positive, some places negative, and it's a mess. So we only want to look at functions where everything ends up positive and defined. But b also can't be 1. If b was 1, then you would have 1 to the whatever. And in all cases, that is 1. So that's not interesting. That would just be the function a. So we just want to make it where it's always defined and positive and not constantly 1. Okay, so as a side note, this is the definition of e. And we'll come back and talk about this more later. But if you take the limit as n goes to infinity, so you let n get larger and larger and larger and larger, and you do 1 plus 1 over n to the n, that ends up approximating this number, which is irrational. So because it's irrational and it's valuable, they gave it a name. And the name they gave it was e. In fact, let me see if I can kind of show you this on the calculator. I've got Desmos open here, and if you do go to ABC, e is e. So you actually can go ahead and do it, and it's there. Oops. So there's e, approximated there. So we go to the next one. Let's do, say, 1 plus 1 divided by 100, and then this is actually the first time I've used this, so we'll figure it out. To 100. So remember, this was the format, 1 plus 1 over a number to that number. So that's at 2.7 already. If we would have done something smaller, 1 plus 1 over, 10 to the 10, we would have been at 2.59. If we do 1 plus 1 divided by 1, let's say 10,000, to the 10,000, I need to stop doing that, don't I? 2.71811459, 2.718. See, we're very close already. This is e, and this is at 10,000. So if we put in, let me put in e again so we don't have to go back. And I won't spend too much time on this. I just want you to see that it does at least appear to work. So let's do 1 plus 1 divided by 1 million to the 1 million. And there we're at, we don't differ here until there. And it's still not much of a difference between 0, 4, and 1, 8. And that's all the way out at the millionth. So you can see as you let that get huge, then it would get really, closer and closer and closer to e. And it might be that I could choose the right number on this calculator, but there comes a point, at any rate on a TI-84, where once you've put in the 1 plus 1 over, say, a trillion, that it just kind of deletes that part, and then it takes the 1 to the trillion and it gives you back 1. So at some point it kind of starts working because the calculator is not able to handle it. But anyway, you can see this is getting closer and closer the bigger the number gets. So that is what e was defined to be. That's why e exists. And again, we'll talk about the reason that we should care about such a thing in a little while. Okay, so my pen marks disappear every time I do anything outside of a page. So this was a times b to the x, where b was positive and not 1. And then we were given this information. This is a little reminder, especially these two, because people get confused about these two and they have to relearn them every single year. And I think that may be in part because the negative exponent leads to a fraction and the fractional exponent doesn't. So I think it mixes people up. But a negative exponent makes it switch position. So x to the negative n is 1 over x to the n. Similarly, 1 over x to the negative n is x to the n. So it just switches position either way. And then the fractional exponent, the bottom one is the root, the top one is the power, and you can do either one first. So this one does the power first, this one does the root first. Okay, so we want to graph this function. This kind of got deleted a little bit. You can see the little hash marks kind of there. So 2 to the negative 3 would be the first thing. So we have x is negative 3 and y is 2 to the x. So 2 to the negative 3. So that's 1/8. And then we have 2 to the negative 2. And the 1/8 came from 1 over 2 to the 3. So this is 1 over 2 squared is 1/4. 2 to the negative 1 is 1 over 2. 2 to the 0 is 1 because everybody to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8. And these you could have put into a calculator if you'd needed to. If you put in 2 power negative 3, it'll give you, well, it'll say 0.125, but that is 1/8. So I'm going to map it. So I go to negative 3 and up to 1/8, which is really low. And then negative 2, and I go to a 4th, which is still pretty low. Negative 1 is 1/2. 1 goes to 2. 2 goes to 4. 3 goes to 8. And I'm going to try to draw a smooth curve through this. It's not very likely that I can, but I could with a pencil, and I hope you can too. That should not have crossed this line down here. I should have stayed totally in the white, but you know. So this will always be positive for the reasons we talked about before, so it should never drop below this as long as it's just a number to a power. Okay, so now we have 1/4 to the x. So let me come over here to the side. 1/4 to the negative 3 is 1 over 4 to the negative 3 because 1 to the anything is still 1. So this is actually 4 to the 3. And there was nothing holy about the 3, right? So this will work for the negative 2 and the negative 1 as well. So this is 4 cubed. And this is 4 squared. And this is 4 to the 1. And now 1/4 to the 0 is 1. 1/4 to the 1 is 1/4. 1/4 squared is 1 squared over 4 squared. And 1/4 cubed is 1 cubed over 4 cubed. So these are the values. So this time I need to get to 64, so let's change this scale. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we'll make these each 8. So I need to go 1, 2, 3, 4, 5, 6, 7, 8. And that's where I map from negative 3. And then from negative 2, I go to 16. And negative 1 to 4 zeros at 1, and these, honestly, I can't even get really low enough to graph them because they need to be below this 1. So pretend they're there, but now this one, if you remember the one before, and you can rewind, if I go back everything will disappear, but the other one looked just like this, but reversed. Like it went, let me change pens. And of course, it didn't have the same scale. It would have had the same scale if it would have been 4, honestly, instead of 2. But, so if this had been 4 to the x, it would have looked like this. So the difference is the number before was bigger than 1, and this one is less than 1. So when you take numbers less than 1 to bigger and bigger powers, then you're multiplying them by something less than 1, so they're getting smaller, smaller, smaller. When you take something bigger than 1 to bigger and bigger powers, you're constantly multiplying by something bigger than 1, so you're getting bigger and bigger and bigger. So the ones that go up are the ones that are bigger than 1, the base is bigger than 1, and the ones that go down, the base is less than 1. Okay, so here's an example that's supposedly true, which may not be. I haven't looked into it since the age of the internet knowing all, so maybe it's easily found to be false. But anyway, this is an exponential question, and basically a situation where someone who knew how exponents work won out over someone who did not. So the fable is this man from India had invented the game of chess as a gift for his king. And the king was so happy that he said, "Ask me any request within reason and I'll grant it to you." And so the man said, "Okay, here's what I want. I want a grain of wheat on the first square and 2 grains on the second square, and so forth and so forth and so forth, and just double it every time and go along all 64 squares on the chessboard." And that seemed fair to the king because he was thinking 1, 2, 4, 8, those are all small, that's not very much. And so he said, okay. So on the first square, he had, well, let's see. So, okay. So the first one he had 1. So this over here, he had 1. And then the next one he had 2. And the next one it doubled. He had 4, which is also 2 times the 2 he had before. So it's now 2 squared. This one he has 8 because he's now taken that 2 squared and multiplied by 2 again because he's doubling every time. The next one he has 16 because he's doubled the 8. He doubled the 2 cubed, which means he multiplied by 2 one more time, so 2 to the 4th. So this continues, and on this one he'd have 2 to the 5th, and then it'll be 2 to the 6th, 2 to the 7th, 2 to the 8th, and he has 63 squares besides the initial one, so he doubles 63 times. So this is going to be 2 to the 63 is what he'll have at the end. So the function is the number on a given square, so we'll just say a sub n, is 2 to the n minus 1. So on the 64th square, he's had the 63 doubles. So what I've written here will disappear when I do this, but I'm going to go put in 2 to the 63. And remember, that's just going to be for a single square. That's not all of them put together. The one before had 2 to the 62. So 2 to the 63, it gives you 9.2233724 times 10 to the 18. So there are actually millions of millions of millions. So remember, million is to the 6th, billion is to the 9th, trillion is to the 12th, quadrillionth is to the 15th. So I guess quintillion? But this would be 10 to the 18th is a million times a million times a million. So just on that one last square, he would have 9 million millions of grains of wheat. So that's a huge number. And you hear people say it all the time, oh, it grew exponentially. And honestly, it's almost always false, and it kind of drives me crazy. But the reason they say that is because exponentially increasing is very rapidly. Okay. Let's go. Okay, so now we have Elaine making a deposit. I gave you the on the page the formulas associated with this, but basically she's going to get 4.25% interest compounded quarterly, which means every 3 months they calculate and add. So if she had $100, they'd give her one fourth of 425, so they'd give her $1.06 in interest at the end of 3 months. And so then 3 months later, they'd calculate the interest based on her having $101.06 instead of just 100. So she's not going to do anything with it for 25 years. So she starts out with 500. So let's look at first the first payment. So at the end of 3 months, or moths, whatever, at the end of 3 months, she has the $500 and she adds to it, I'll write this out first, she adds to it $500 times the percentage she gets for that 3 months. Well, she gets 0.0425 for the whole year, but she only gets a fourth of it now because it's only been a fourth of a year, so she gets a fourth of the interest. If I factor out the 500, because obviously I don't want to do this calculation 100 times, so I'd like to find a pattern, so let's make it as clean as possible. Factor out the 500 and I get 1 plus 0.0425 over 4, whatever that may be. At the end of 6 months, she still has, this is her new investment value, right? This is how much money she has in the bank at the end of that 6 month. And that gets also multiplied by this scalar, because this is the thing that you multiply whatever you invested by. In our case, it was 500 before. Now it's this, whatever this is. This, like, I don't know, 505 something is sitting there now and getting multiplied by this. So I've multiplied by it twice now. So if I'm trying to make a pattern, I'm not going to want to write anything 100 times. So let's note that this has now been multiplied by this twice. That's interesting. I'm off my slide. Okay, so at 9 months, she's got her 500. She's multiplied by this twice already. And now she's going to multiply by it again. I'm writing weird things because I'm distracted by the jerkiness of my pen. So now she's multiplied by it 3 times. So when I'd had 1 compounding period, I multiplied by it once. 2 compounding periods, I multiplied by it twice. The 3rd compounding period, I've multiplied by it 3 times. There's a pattern here. Okay? So for the full amount, the total amount she's going to have left at the end, she's going to have her $500, and she's going to have multiplied by 1 plus the portion of interest she gets in a compounding period, which is the interest divided by the number of compounding periods per year, to the power of the total number of compounding periods. 25 years, 4 for each time, that's 100. So this is how much she has. Note that this is the amount you put in, which as of last year you were referring to as A, times 1 plus the annual interest rate divided by the number of compounding periods per year, because this is just the portion of the interest you would receive at that compounding period, raised to the total number of compounding periods. So the way you do that is say, how many do I have per year times the number of years. So this is the general formula for these calculations. And so now that we have all this down, it's going to disappear for a minute because I'm going to go find out how much money Elaine has by going into Desmos. So Elaine has $500 times 1 plus 0.0425 divided by 4 to the power of 100. She has $1,438.71. $1,438.71. $1,438.71. So not bad. 25 years is a long time, and good luck finding that interest rate, but that's a pretty good return. Okay, so now John's going to put $500 into an account bearing 2.5% compounded monthly. I'm going to change pen colors just out of boredom. Okay, so he puts $500. 2.5% is 0.025. I'm always going to move the decimal twice. Divided by compounded monthly means I have 12 compounding periods per year. So I put in a 12 there. And then the question is, how much will he have in 25 years? So he's going to have 12 periods per year for 25 years. So this is going to be 500 times 1 plus 0.025 over 12 to the power of 300. Okay, so that is now what I need to go put into Desmos to find out what John is going to have. So he's leaving it the same amount of time she is. He's got a much, much lower interest rate though. But it's compounded monthly, so that'll cancel out some of it. So John has 500 times 1 plus 0.025 divided by 12 to the power of 300. So he only has $933.52. $933.52. Why that switched back to red? Okay, so that's how much John has. Now Jennifer's going to put $500 into an account bearing 3.2% interest, so that's kind of in between. Compounded continuously. How much money will she have in 25 years? This is when we're going to get back to the definition of E. Okay, so let's look real quick at the formula that we had. We had whatever you invested times 1 plus the rate over N to the NT. So let's look for just a moment at this part. This doesn't look too different from the definition of E. So here's another thing. If you take the limit as n goes to infinity of 1 plus 1 over n to the n, you get E. But as it happens, if you take the limit as n goes to infinity of 1 plus x over n to the n, you get e to the x. And that happens, that's mathematically factual, okay? So this is why E gets a name. Because you have these sort of rates of increase that look like this in the very natural, clear way that we kind of derived previously. And this is on a 1 year or 1 day or whatever the time period is type of situation. But if your compounding periods are constant, so you don't have one a month or one a quarter or whatever, but you have constantly compounding, like the growth of bacteria, the spread of fleas, rabbits, things like that, and that are sort of continuously increasing at a given rate, then what happens is you have compounding time all the time. So your number of compounding periods per year gets larger toward infinity. N, remember, was the number of compounding periods per year. So if N is getting arbitrarily large as you compound all the time, then this 1 plus r over n to the n, which looks very much like this, the limit as the number of compounding periods now goes to infinity, is 1 plus r over n to the n is e to the r. So if I have a times 1 plus r over n to the nt, that's equal to a times 1 plus r over n to the n, all of that to the t, because when you have exponents multiplied together, you can pull one out, and if you have one out, you can pull it in, so this is equal. So as n goes to infinity, this part here goes to e to the r. That's where this comes from, a e to the r, and this would be, of course, to the t, but that's a e to the rt because of the properties of exponents. So that's where this comes from. And generally this is a p, and people memorize pert. But for your purposes, I believe next year you'll still be using a. You will revert to the p as 11th graders, I should mention. But so a times e to the rt when it's continuously compounding. So this one's actually the easiest one to plug in, but maybe the most difficult to introduce, but I don't like just giving you a formula and not kind of explaining why it works, because it's a lot harder, I think, for people to understand math if it looks like magic. And since E is defined to be the guy that does this super handy thing, people feel like it's just, oh, look at that, that number did that thing. No, that number has a name because it does that thing. So anyway, I don't know if I have room to write on here anymore, so I'm going to go backward and then forward again so that I have plenty of room to figure out how much money Jennifer has. Okay, so for her, all we have to do is 500 times e to the 0.032, so that's r, t, 25. That looks like a C, but it's not. Okay, so here we go. She has 500 times e to the, and by the way, I'm just typing these now instead of going back and forth. I don't know how to make it do an exponent without typing, but I just typed the letter e right there, and it's going to know exactly what that is. 25 times 0.032. So she has 1112.77. So 11, 12, 77. Okay, so now we have a colony of bacteria. So this is another thing. Bacteria grows at an exponential rate like a continuously compounding investment. And things like carbon-14 decay at an exponential rate. It looks exactly the same. It's just that if you're growing, you have a positive rate, and if you're decaying, you have a negative rate. But it's the same formula. Let's see if cyan is blinding. Okay, so we have the bacteria growing at a rate of 10% per day. And today, there are 5,000 bacteria. So the question is, how many will there be in a week? Because the rate is given in per day, T is also in days. So whatever the rate is given in, if you're doing financial stuff, it's almost always annual rate of. This one's a daily rate, so T is going to stand for days instead of years. So we have 5,000, that's how much we started with, times E to the rate, which is 0.10, times the number of days in this case, so 7. So this is 5,000 times e to the 0.7. (5,000) times e to the 0.7. So 10,069. So in previous ones I was rounding to the hundredths, because it was money, so it's cents. In the case of a bacteria, not so much going to have a partial bacteria, so we round to the nearest whole. So 10,069. So we've more than doubled our bacteria, which might be good if we're trying to grow it, but certainly isn't if we're sick. Okay, I guess that's the end of the slide. So hopefully you have learned a bit now about the exponential functions, and there was quite a lot written for you also on the page, and there are also other videos and resources that you can access, and then I will get you an assessment posted soon.